Today we're going to look at LeetCode question number 42, trap in rainwater. Given n non-negative integers representing an elevation map, where the width of each bar is 1, compute how much water it can trap after raining. So if we have this example here, we can store a total amount of 6 units of rainwater over here. You can see on this graph. So what actually determines if we can trap rainwater at a certain position? So let's look at position 0 here. Can we trap any rainwater here? Well, no, not really. That's because what determines the amount we can trap is the left border and the right border, because we need a container. No matter how high this bottom part is here, we still need the edges to help us be able to trap the rainwater at this position. So for example, at 0, on the left, we don't have any boundaries or edges greater than this height of 0 here. On the right, we do. We can try to trap rainwater, but it'll just leak out over here on this left side anyway. What about for this boundary here? Can we store any rainwater up here? Well, we can't, because again, we don't have a left edge higher than this position here. So whatever we try to trap up here, it'll just spill out. What about this guy over here? Well, we can't trap water because on the left we have this edge of height 1, so we can fill it to 1. But let's look at the right. We have of height 2, so we can try to fill it to 2. But even if we do fill it to 2, it'll all leak out and we'll just end up with a height of with a 1 unit of rainwater filled anyway. So we can kind of see our limiting factor here would be the heights between the edges of any position. So what we can determine here is to get the rainwater amount, we need the min of the left height and the right height. So let's look at this guy here. Can we try fill in any rainwater here? No, we can't, because on the left we don't have any edges greater than or equal to, so there are none. On the right, no, we don't have any either. What about this guy over here? This height over here? Well, we can, because the left edge boundary has a higher height than this one, so we can trap here. Oh, and let me re-explain this one. While this one is of higher height, we can try filling of this height, but it'll just all leak out here anyway. And what about this one? Yeah, we can, if we look at the left edge, we can fill up to this height. If we look at the right edge, this is the highest one, so we can try to fill up to this height, but it'll be pointless anyway, because this is smaller. So we'll just wind up filling rainwater to this height anyway, and so on. So we can see the equation is to get the minimum of the left largest value and the right largest value, and minus it by the height at that position we're looking at. Okay. So that's basically the equation here. So I can show you. So how can we solve this? Well, one brute force way is for any position, like here, for this position here, we're at position 0. We can traverse the array to find the largest on the left side and the largest on the right side. Oops. Largest on the right side, get the minimum of those two and minus it by the height we're looking at. But this will end up being O of n squared time, because for every, as we're traversing through the array, looking at each elevation, we're also traversing through the array again towards the left and the right. So it's a nested loop there. So it'll be O of n squared. There's a better way where we can use two storage arrays. So if we have our height array here, and this height array is 0, 1, 0, whoops, 1, 0, 2, 1, etc. We can have a min array and a max array. Or sorry, not min or max, a left array and a right array. So where basically we traverse the array in the forwards direction to look for the maximum height and then store it in this left array, and then traverse through the array in the reverse direction and keep track of the maximum right array or right elevation that we see so far. So for example here, left, our maximum left we see is 0, so 0, and here the maximum right we see is so far is 1, so 1, and here the maximum height that we see on the left is still 1. Here the maximum we see is 2 now, so this is 2, and here at 1 we still have a maximum of 2, and so forth. And for right we do similarly, so this is like 1, so maximum we see so far starting from the right side is 1, and then maximum we see so far is 2, and then over here still 2, over here still 2, and then 3, and then it'll be 3 for the rest of them. And then using that we traverse through this height, we traverse through the height array, and we use this formula to get the min of the left and right here, and minus it by the height we're looking at. So for example here the minimum is 0, so 0 minus 0 is 0 rainwater trapped. Here minimum, let's look at this one. So what we're looking at right now is 0 here. The minimum between left and right is 1, so 1 minus 0 is 1. So we can trap 1 rainwater at this height here, which is actually consistent. You can only trap 1 rainwater here. Okay. 0, 1, 0, 2. Yep. But this does take, while this is O of n runtime, this takes O of n space because we're keeping track of these two arrays. A better way is using O of 1 space, using 2 pointers. So basically what we're going to do here is only be able to traverse through this array once instead of like twice here, or 3 times. And then we keep track of a max left pointer, max left, and then max right pointer. And then we're going to have a regular right pointer and a regular left pointer. Okay. And what we're going to do in this case is, so we're going to determine what the minimum is between the max left and max right. And whatever the minimum is, that is our limiting factor for the boundary. And then what we're going to do is whatever the minimum is, we're gonna increase this left pointer here. Whatever the minimum is between this maximum left and maximum right, we're gonna increment either the left or right. So for example, if the maximum right is smaller than maximum left, we're gonna increment the right pointer, okay? And then we're gonna use this formula, or actually we're not gonna use this formula. What we're gonna do, since we already know this here, this guy is smaller, this is gonna be the limiting edge. So what we can simply do is do max r minus the regular r pointer, since we already know this is like the smallest guy. Okay, and similarly we're gonna check. Okay, and also if it turns out this right here is greater than this maximum right, we update maximum right. And similarly for the left side, so if if we're traversing, so let's say that this is the max left we found so far, and this is the max right we found so far. So what we're gonna do is traverse our regular left pointer here, and since or actually sorry, we're gonna traverse this, since this is a smaller, we're gonna traverse our regular right pointer here. Okay, and since this is already the limiting edge, we're gonna do max r minus min r, and since it turns out that this value is going to be negative anyway, we just ignore it. We just round it up to 0 and say it's 0. Okay, and since this is higher than max r, we're going to update max r to be here. What about the case max left and max right are the same? Well, it doesn't matter which one we move anyway. We can move this guy here, or this maximum, or we can move the regular left pointer here or the regular right pointer here. It doesn't matter. Okay. Now what if it just so happens max r is here? Well, since this is smaller, we're going to move our regular left pointer here. Okay. And then we're going to do maximum left minus regular left. Why not maximum right minus regular left? Well, because we know that this guy is already smaller. So this is going to be the limiting edge. Okay, and then we do that equation there and then add it to our final result. And when we finish when the regular left and regular right pointer meet. Okay, now to code this up, what we're going to do is initialize our left max pointer and right max pointer. Initially, they're going to be at the very left and very right of the height array. And similarly, our regular left pointer and our regular right pointer. And these will just traverse through the height array or explore. And while left is less than right, we're going to check first if height left max greater than or equal to height right max. What we're going to do is increment our regular left pointer and get the rain water trapped by doing that. Because remember, this guy's our limiting edge for the container. Okay. And we increment the left and that's okay if you increment the left. We start at the edges anyway when we initially go through the array, so then it'll be here and here, and the edges always can trap 0 rainwater because there's no edge to the left or right that can help them trap it. Okay, and if rainwater trapped is greater than 0, and I need to initialize my result. And result plus equals rainwater trapped. Okay. And finally, what we have to do here is if our current left pointer, left position, if height left greater than height left max, update left max to the new height position. And we do the same thing here. If if the right max is greater than left max, so we do right minus equals 1, and rainwater trapped equals right max and if rainwater trapped greater than 0, then we increment. And finally, we update height right max if the current right pointer is at a greater position. Is at a greater value. If height right okay, and finally after all that we return result. Okay, I'll start compiling. Okay, I'll check the rest of the test cases first. I'll submit. Great, thanks for watching.